So guys, we're going to be discussing Cambridge IGCSE February March 2026 paper 4.2. It's a 1 hour 15-minute paper, but we're going to go through it in a comfortable pace so that we know how to solve all of the things. So let's start with the first question. It's pretty straightforward. A student cycles from home to school. Figure 1.1 shows the distance time graph for this journey. So it's a distance time graph. That's the number one thing we have to keep in mind. So the gradient represents speed. So let's remember that. Del change in distance by change in time is equal to speed. So that's very important. That being said, now we can, before we even go into the question, we know that there's a certain speed here, and then a faster speed here, lower speed here, and then stops between D and E. So that's basically the approach that we're going to take, right? And the distance covered is obviously going to be whatever this value is eventually. So this looks like approximately 1.7. All right. So state the distance between home and school. So the distance is going to be 1.7 kilometers. I think that's pretty straightforward. Keep in mind to take a good look at the units whenever you answer these questions. 1 point A, B, C, D, E, well, a time identifies when the student accelerates. So acceleration by definition is when the speed is increasing, right? Or rate of change of velocity is acceleration. So and we've got decelerates where it slows down. So it's speeding up at some point and slowing down at one point. So you're traveling at a speed of this, and then you end up at a speed of this, which means your speed increased, which is indicating that you accelerated at B. And then you are traveling at a speed of this, and then the slope decreases, which means your speed again decreased. So you decelerated here. So here you accelerated, and here you decelerated. So answer is going to be student accelerates at B, student decelerates at C. There you go. 1.1 to calculate the student's maximum speed in kilometers per hour. So if we want to find the maximum speed of the student, what we do is we identify where the graph has the steepest part. And that's pretty obvious to be between C and B. So you have to find the gradient at this point, right? So if you want to find the gradient here, we do a calculation of that would be, so we use the equation, the speed, as we just said, is basically del D by del T, which is, in this case, distance is your y-axis value, time is your x-axis value. So it's going to be y2 minus y1 divided by x2 minus x1, which gives you a total of 1.25, you could say. We're basically taking this point. This is 1.25. And we're going to take this point, which is 0.4, minus 0.4 divided by x2 and x1. So C here and C here, which is 7.5 and 5. So this is going to become 7.5 minus 5.0. So that gives them, if you do the calculation, you're going to get a speed of 0.34 kilometers per hour. Keeping in mind that the units are in minutes on this side and it's kilometers on this side. So you have to convert this into hours, right? So if we do convert that into hours, how much does it come into? So 7.5 minus 5.0, that's the number of minutes. So we do a quick calculation where it's going to be 1.25 minus 0.4 divided by 7.5 minus 5 is 2.5 minutes. So 2.5 divided by 60. So we're basically converting it from minutes into hours. So that gives you a speed of 20.4. So you get a speed of 20.4 kilometers per hour. So that's how you solve this. That's your method of solving this. All right, let's move on to question number 2. Figure 2.1 shows a ship made of steel floating on the sea. Okay, so that's a carrier ship. Those are little containers. God knows where it's going. So, by the way, I think it's traveling this way, yeah. Anyway, so state the direct equation that links density, mass, and volume. So density, I'm sure everyone knows, is mass by volume. Easy peasy. And you can write it, if you want, you can even write it as density is equal to mass by volume. That's also fine. Density of steel of 7,000, steel is 7,900 kg per meter cube. The mass of a solid steel cube is 110 kg. Calculate the volume of the steel cube. So we just use the formula, density is equal to mass by volume. So volume is equal to mass by density. So mass is 110 divided by density 7,900, which gives us a volume of 0.0139 meter cube, if my calculation is correct. Yes. All right. Let's move on. Next question. Density of seawater is 1030. State why the solid cube sinks when placed in seawater. It's because, very simply put, it has a greater density than seawater. So that's all you need to write, that the density of steel's density is greater than seawater. That's it. Make sure you don't write it in shorthand like I just did, but make sure you write it nice and clear. Explain why the steel ship in figure 2.1 floats on water. So what happens is, if you look at the ship, the structure of the ship, the steel is basically on the outer border, right? Pretty much. Most of the interior of the ship is empty, or it's air. So the average density of the ship overall is less than the density of water. So that's what you have to write. As the ship's interior is empty or full of air, so the ship's interior is full of blah blah blah, full of air, and hence average density is less than density of water, so it floats. So density of steel, as you can see, is 7,900. Density of water is 1,000. Density of air is about 1.3 kg per meter cube. So when you do the average of air and steel, you get a very low density, much lower than water, and that's the reason why it floats. There you go, easy peasy. Right, let's move on to the next part. The mass of the ship is 3.5, blah, blah, blah. The ship accelerates 0.75. Calculate the force which causes this acceleration. So F is equal to ma. So we need the force, and the mass is 3.5 times 10 to the power 7 into the acceleration, which is a very small value, 0.75 meters per second squared. Always make sure you have the right units. So if that's the value, then your answer is going to come around 2.6 times 10 to the power 7 newtons. Explain why the force provided to the ship's engine must be larger than the value in B2. So again, if we go back to our ship, as the ship is traveling this way, it will face resistive forces, massive resistive forces due to the friction with the water, and also some resistive forces with the air. So to accelerate at that value, you need the resultant force to be the value that we calculated as 2.610 times 10 to the power 7. However, they were going to have a massive resistive force. So the overall force that the ship has to generate to move forward will be more than this. So this plus drag, that's going to be our total output force. So that's basically going to be your answer, that there is drag acting on the ship, right? Drag from where? From the water mainly. And if you want to, then you can say from the air, which is air resistance. Hence, drag acting or water and air, blah, 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 in the opposite direction or in opposite direction, or you can say opposing, whichever way you want to write. Hence, greater force is required. Force to overcome. There you go. Let's go on to question number 3. So what do we have in question number 3? We've got a polar bear and we've got a person, both on 2 pieces of thick ice. Contains information about the polar bear and the person. Okay, very nice. Do polar bears eat people? I think they do. Yeah, they are carnivores, or yeah, omnivores? No, carnivores. No, they do have seaweed sometimes. So yeah, omnivores. Anyway, avoid polar bears. So calculate the weight of the polar bear. So you've got the mass of the polar bears. That's pretty much a no-brainer. W is equal to mg. So that's 590 into 9.81. That gives us a total value of, so here's the thing. So if you calculate this, you're going to get 5787.9. But this is 1, 2, 3, 4, 5 sig fig. So we don't write 5 sig fig, right? Because our question has, you could say 3 sig fig, 2, 3 sig fig. So you should write it 3 or 4 sig fig. So This would be correct if you write 5787 or if you write 5790, but nothing more, nothing less. Right, let's move on. Calculate the pressure that the polar bear exerts on the ice. So for that, we need the pressure and the area. So the pressure is basically the weight of the polar bear. Pressure is equal to force by area. So the force is basically our value. Here, what we do is we always use the raw value, right? The calculated value. We don't use the answer value because we rounded it off. So we're going to use this. So it's going to be 5787.9 divided by the cross-sectional area. So polar bear area in contact with the ice is 1.12. So that's going to be our area. We're going to write here 1.12. I don't like the red, to be honest. 5167.76. Again, 1, 2, 3, 4, 5, 6 sig pig. We're not going to write it to this. We're going to write it to 3 or 4 sig pig. So our answer is going to be 5168 or 5170. That's our answer. All right, let's move on. Use the numbers to complete each equation. So we've got a bunch of numbers here. Change color. And we're supposed to do the calculations. So number one, mass of the polar bear dash times mass of the person. So what we have to do here is we need to find out how much is the mass of the, how many times is the mass of the person less, or how many times is the mass of the polar bear more than the person. So it's going to be mass of person, mass of polar bear, which is basically 590 divided by 84. That's going to give us the ratio. So 590 divided by 84. So if you do this calculation, you should get 7.02. So which is basically 7. So you can write 7. So the polar bear is 7 times more massive than the person. Area of contact of ice is the number of times area of contact of ice of the person. So again, what we do here is we do the calculation of 1.12 divided by 0.02. So 1.12 divided by 0.02, that gives us approximately 56. We've got 56 here, we write 56. Pressure exerted by person into pressure exerted by polar bear. So here what we need to do is pressure is equal to force by area. So we do the force calculation for the person because we've already done the pressure calculation for the polar bear, which is 5170 or 5168. So for the pressure of the person, if you do the calculation, it's going to be mass of the person 84 into 9.81. That's the weight of the person divided by area 0.02 or 1202. So number of pressure exerted by person is how many times more than the polar bear? So a very easy calculation. We just go back here because we're running out of space. So 41202 divided by 5168, right? If you do the calculation, you will get approximately 7.97, if I'm not mistaken, which we can say is approximately 8. So you write 8 as the answer here. There you go. Under the ice is seawater, which has a density of this. Calculate the change in pressure between the top of the seawater and a depth of 2.5 meters. This is pretty easy. So del P is equal to rho G del H. That's a rho. I'll write it nicely again here. So rho G del H. So rho is the density of seawater. It is 1030. G is 9.81. And our height is 2.50, which gives us a value of, to be exact, 2526, 0.75. Zero is weird. I'll put it nicely again. So again, when we write this, 2 or 3 sig fig. So even if I write this to 3 sig fig, I can't write the 6. I know a lot of people would love to write that or are itching to write this part, but you can't. So your answer is going to be 25300 pascals. That's because your values are in 3 sig figs, the question values, so your answer values have to be 3 sig fig also. All right, that's that. Done with question 3. Let's move on to question number 4. What's this weird thing? Anyway, okay, that's a person. Okay. Why is this person's head so small compared to his body? His head should be bigger. Nah? At least something's going on. Be bigger on this side. Anyway, we're here to do physics. State method of thermal energy transfer that warms the people. So there's an outdoor heater. So there are three methods of conduction, convection, and radiation, right? So air is a poor conductor, so we're not going to consider conductor as a method by which air is going to them. It's not going to be convection because convection is going to cause heat to go up. So your answer is radiation. So radiation is what's causing energy transfer. So your answer is going to be radiation. That's your answer. Moving on. Complete the sentences about energy transfers from that warm the table. The heater transfers energy to the dash store of the table. Store. Okay, yeah. You could say thermal or heat store of the table. The temperature of the table increases. The rate of energy dash by the table is greater rate of energy by the table. So gained or absorbed. Rate of energy absorption. Absorption by the table is greater rate of energy emission by the table, and transfers energy to the thermal store. Okay, yeah. Basically, it's thermal energy stored in the table. That's why you get this as the answer. One of the people puts a white cloth over the table. Explain why the white cloth causes the temperature of the table to decrease. So basically, the reason is the main energy transfer method is radiation. And a white cloth, if you put a white cloth here, oh, so much going on here. So if you put a white cloth here, then what's going to happen is it's going to reflect off the thermal energy. So it's going to reflect off more. So basically, the explanation is that putting a white cloth over the table increases radiation being reflected and decreases absorption. Thus, temperature is less, or heat energy absorbed is less, hence temperature is less. All right, then moving on. Let's use a different color. Let's go to green. I think green is nice. The heater has a power of 2.5 kilowatts, switched on for 3 hours, kilowatt hours, 2.5 into 3. The calculation is energy used is power into time. In this case, if we're using kilowatt hours as a unit of energy, then the power has to be in kilowatts and the time has to be in hours. So 2.5 kilowatts used for 3 hours. That gives you 7.5. That's your answer. 7.5 kilowatt hours. There you go. Let's move on. Question number 5. Atmospheric pressure is 1.0 times 10 power 5 Pascal. A volume of 1.02 meter cube of air, atmospheric pressure, is pumped into a car tire. Pressure of the air when it is inside the tire is this. Calculate the volume of the air when it is in the car tire. So, yeah, what you're doing is we have atmospheric pressure. What the values they've given us is atmospheric pressure, volume of a tire, and pressure of the air when it's inside the tire. So calculate the volume of air when it is in the car tire. So we use P1 V1 is equal to P2 V2. So the values you have is, for example, atmospheric pressure is this. So you've got pressure in the atmosphere, right? Volume of this 1.2 of air, atmospheric pressure. So we've got V1. We've got the pressure of the air inside the tire, which is P2, and we're just supposed to solve to find the value of V2. Pretty straightforward calculation. So V2 is equal to P1 V1 by P2. So that is basically, if we just put in all the values, it's going to be 1.0 times 10 to the power 5. It's 10 to the power 5 into V1, which is 1.02, divided by pressure in the tire, which is 2.6 times 10 to the power 5. So if you do your calculations, it should be 0.392 meter cube. That's your answer. Describe the structure of a gas in terms of separation, arrangement, and motion of particles. So I've always mentioned that whenever you talk about this, be very specific about each one. Don't write anything else. It's only 1 mark per explanation. Number 1, separation. So you can say large intermolecular spacing. Large intermolecular spacing. Arrangements is no arrangement. There's no structure, right? So you can say no arrangement or you can say random. Both are correct. And motion. So you can say constant random motion And here what I love to add is along straight lines with zigzag, or just along zigzag paths. So why I say zigzag is so that you understand that it's moving along straight lines, and there's only a random change in direction when it collides with something. So it's not like random, like a squiggly line like this, but it's like this. Do remember that, right? And no, that's not a star. The pattern you draw should never have any sort of recognizable pattern in it. It should be completely random. Explain in terms of particles why the internal energy of the gas decreases when the gas is at lower temperature. So that's pretty straightforward, because internal energy is the combination of a gas's molecular kinetic energy and molecular potential energy. So here, the molecular kinetic energy is part of internal energy. And decreasing temperature decreasing temperature leads to lower molecular Ke, and thus to lower internal energy. That's it. So 2 marks for 2 points. One is that decreasing the temperature causes the particles to lose Ke, or lower speeds, whichever one you say. And the next point is obviously that the molecular kinetic energy decreasing means the internal energy is also decreasing. All right, let's move on to the next question. 6.1 is a full-scale drawing of object O, thin converging lens L, and image I of object O. So, okay, fine. Identify Z. Where's Z? Okay, so Z is basically this line, which is the principal axis. All right, so yeah, principal axis. Determine the focal length L of the lens. Show any working space provided or on figure 6.1. So how do you find the focal length? So as they said, it's a full-scale drawing. You have to use a scale and a pencil. So what you should do is you draw the two rays. So one ray is this one, which goes dead straight. I'm not using a scale, but that's what you should draw. Should be straight. And another line should go straight, parallel to the principal axis, parallel to this line. And then you draw it to the top of the image like this. So this is the focal point. And if you want to, just for clarity, you can do the same thing on this side. And you draw this. A little bit of error here, but this is also the focal point. So the focal length, you take a scale and you measure this distance from the mid of the lens, from this line up to here, or from the mid of the lens to here, whichever one you count or calculate. And that should give you an answer of apparently 1.8 centimeters. I don't know really, you have to do the maths, but that's the idea. The image in figure 6.1 is inverted. State two characteristics of the image. So, well, we can obviously see that the arrow here is pointing upwards and the arrow here is pointing downwards. So that basically means that it's inverted. So they're asking for two other properties. So another property, okay, let's write inverted. Next is it's real. How do we know it's real? Because rays of light really actually travel along this path and then they all meet here. So it's real. And number three is, if we take a good look at the diagram, you'll notice something. The length of this is the same as the length of this. Make sure you use a scale. Another way of identifying this is the focal length that you're going to calculate is going to be exactly half of this total length. Should be half of this total length. Also on this side. So basically the object is at 2f. If that's the case, then it will always be the same size. All right? And that's how we know that these are the two properties. So what are the two characteristics? It's going to be real. It's going to be the same size. All right, let's move on. Next, different converging lens with focal length f. Lens 6.2 used as a magnifying glass. Position of blah 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 blah. Draw position of an object which produces a magnified image. So the object should be less than f. So if we put it like here, and then just for the sake of it, I'll just draw that again like this, and another ray like this. So if you do dot 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 dot, dot, these are virtual rays. We get an image here. This is our image. This is our object. Image is virtual, magnified, and upright. So virtual, magnified, and upright, right? And this is how you use it as a magnifying glass. And an observer here would see it. Like that's a big eye, yeah. So, two statements. Magnified image. On the opposite side, no. Same side, yes. Same distance from the lens, no. Closer to the lens. Is it closer to the lens? No. Further from the object. Yes. So these are the two statements which are correct. Right. And that's what we can see very clearly from the diagram. But let's move on. Question number 7. Figure 7.1 shows two identical cells in series with a thermistor and a fixed resistor. So these are two identical cells, all right? Switch is closed. The reading on the voltmeter is 9 volts. So 9 volts is basically measuring the EMF of the two cells together. The reading on the ammeter is 4.6 milliamperes. Determine the EMF of one cell. So very, very common mistake. You might end up writing 9, but it's not, because 2 is 4.2 is 9. So each one is 4.5 and the unit is volt, obviously. Let's rub all of that out. We're going to need space. Complete the sentence to define electric current. Electric current is the amount of dash passing a point per unit dash. So that's charge per unit time. I'm assuming they might also accept second units. Nah, I don't think you should write second unit time. Charge per unit time, coulombs per second, basically. Then the resistance of the fixed resistor is 480 ohms. Calculate the resistance of the thermistor. So how do we do that? So take a look at this. What is the information we have? So we know that this is 4.6 milliamperes. So this is 4.6 milliamperes, so 10 to the power minus 3. And we know the voltage is 9 volts. So we can find out the total resistance of both of them together, because V is equal to IR. You'll see you'll always end up using V is equal to I. So R is equal to V by I. So V is going to be 9 divided by our current 4.6 times 10 to the power minus 3, right? So if it's 4.6 times 10 to the power minus 3, what is our total resistance? We'll get it as, that's going to be 1956.5. So 1957 or 1956.5. So we know 480 ohms is the resistance of one resistor. So this is 480, and in combination it's 1956.5. So what's our total resistance going to be? 1956.5 is equal to 480 plus X. So X is going to come out as minus 480 is equal to 1476.5. So you can write 1477 or 1480 ohms. That's your answer. There you go. Next. The thermistor is placed in a beaker of ice. The temperature of the thermistor decreases. State how this change in temperature affects the readings of the voltmeter. So let's first sort this out. If the temperature decreases for thermistors, basically the resistance will increase. So temperature decrease will cause resistance to increase. In normal metal wires, it's the other way around. But for thermistors, if the temperature decreases, resistance increases. So if this resistance goes up, it will increase the resistance in the circuit. Voltage will stay the same because the voltage is 9 volts due to the batteries. That's not going to be affected. But your resistance has gone up, so your current is going to go down. I is equal to V by R. That's another way of putting it. Easy to remember, V by R. So V is same. R just went up. I must come down. So that's how we solve to find the new current. So what's going to happen? The answer is voltmeter reading, no change. And ammeter decrease. Because, no, they didn't want an explanation, but I'm just saying it, resistance increases. That's right. All right, that's question 7 done. Let's move on. Question number 8. A transformer steps down high voltage electricity. The transformer has 6,200 turns in the primary coil, 43 turns in the secondary. Let's just quickly draw this. It's easy to visualize. So we've got primary 6,200 primary, and we've got 43. Let's put some loops here on secondary. All right, calculate the input voltage. The output is this. So the formula is voltage in primary divided by voltage in secondary is equal to number of turns in primary divided by number of turns in secondary. VPVS is equal to NPNS, right? So if you do the maths, we're basically trying to find voltage in input voltage. So we're trying to find voltage in primary, which is NPNS into VS. So that's going to be number of turns in the primary, 6,200 NP divided by number of turns in the secondary, which is 43, into VS, which is 230. Right? 230. So your answer's input voltage is going to be, well, the raw value is 33162.79. Again, we don't write any of that. We write a maximum of 2 or 3 sig fig. Because the values here are 2 sig fig, you can write it up to, 2 or 3 sig fig. So I would write 33200 volts. That's it. Or you can just write 33000 volts. That's also fine. 2.2 kilowatt kettle is connected to the secondary coil of the transformer. Calculate the current in the primary coil of the step-down transformer. Assume the transformer is 100% efficient. So now we use the same formula, or a similar formula actually. So VP, the formula is V, conservation of power. That's what we have to use here. Is power in the primary, P voltage primary, VPIP is equal to VSIS. So where is this coming from? P is equal to IV. So we're just using IV here. The power in the primary coil is equal to power in the secondary coil. And they said that kettle is 2.2 kilowatts, so that's going to be the power in the secondary coil, which is also equal to the power in the primary. So we can write basically voltage in primary, which is our previous value, this massive value, is into current in primary is equal to VSIS. VSIS is equal to the power. So we write voltage in current in primary, that's what they want, is equal to VSIS. So we can write power in secondary divided by VP, voltage in primary. Power in secondary is 2200 divided by voltage in primary. Voltage in primary is 33162.74. And if we do the maths, it's going to be 0.0663. So we can write 0.663, or you can just write 0.066, whichever one you're comfortable with. Power station produces 1.3 gigawatts of electricity. Transformer at the power station steps up the voltage before the electricity is transmitted. This reduces the power loss during transmission. State the equation for power loss in electricity transmission. So because we've got power supply and we've got resistance, so we can, for electricity transmission, we can use P is equal to I square R, which is basically the current in the wire squared multiplied with the resistance of the wire. And explain how step-up transformer reduces the power losses during transmission. It's very easy. Step-up transformers increases the voltage and decreases the output current. And because there's a decreasing current, according to the formula, lower current means lower value of I square. So the power output will, or the energy loss due to the heating effect of the wire, is going to be decreased because power is equal to I square R. So less current, which means less power output. So in simple terms, you increase the voltage, you decrease the current with a step-up transformer, and the current is, the electrical energy is transferred through the wires at this low current, high voltage, and this low current prevents energy loss in the wires from heating because you decrease the current. So P is equal to I square R. That's pretty much how we do it. Right, moving on. Question number 9. Figure 9.1 shows a beam of alpha particles and gamma radiation entering an electric field between two charged metal plates P and Q. Figure 9.1. Draw the path of the alpha particles inside the field. Label this alpha. Gamma radiation inside the field. Label this gamma. So let's draw gamma first because it's kind of straightforward. It's literally straightforward. That's it. And that's going to be gamma. And then let's draw alpha. Alpha will be repelled by the positive plate and it's going to be attracted by the negative plate. So the path will be basically like this. So you can make it hit the negative plate, or you can also make it curve and then leave at a straight line. Both are going to be assumed to be correct. So this can be alpha or this can be alpha. That's the idea. Student places a sheet of paper in the path of the beam before it reaches the electric field. State how this affects alpha and gamma radiation of the electric field. So alpha will be stopped because paper stops alpha, and gamma will be unaffected because gamma is so penetrating that it does not even sense the presence of the paper in its path. The beam of alpha particles and gamma radiation, figure 9.1, is replaced by a beam of beta particles. State and explain the path of the beta. So beta is negative, right? Alpha was positive. That's why alpha got repelled by the positive plates and repelled by the positive and attracted by the negative plates. Beta, on the other hand, will experience a very different path. Beta will, you'll see two changes with beta. Number one, you'll see beta bending towards the positive path, and number two, the bending will be much more. Why? Because beta is 8,000 times lighter and half the charge. So even though it's half the charge, because it's 4,000 times lighter, sorry, 8,000 times lighter, so it's going to actually bend much more. So your answer is going to be beta will move towards the positive plate or move upwards. Beta will move upwards, and beta will move upwards. And the second point is that the mass is less. Oh, sorry, it's negative. So because it's negative, it will be deflected in the upward direction towards the positive plate, attracted by positive, repelled by negative, and also it's going to bend more bending because it is much lighter. So yeah, there you go. That's your done answer to question number 9. All right, let's move on. Question number 10. Planetary nebula form as part of the life cycle of stars. Complete the sentence about a planetary nebula. Okay, fair enough. Stars expand when they run out of hydrogen to fuel nuclear reactions. A dash forms a planetary nebula. Well, a star, yeah. What type of star? So what's right before planetary nebula? We can say a red giant. Red giant star, okay, fine. State what is at the center of the planetary nebula. So once you've got the layers thrown off from the star, right, as they're throwing off, you're left with the core. And what's the core? For a star which is sun-like, or stars which form planetary nebula, this will always be a white dwarf. There you go. Moving on. Planetary nebula emits blue light and red light of two specific wavelengths, 5.0 times 10 to the minus 7, 6.6 times 10 to the minus 7. Explain why the light with wavelength 5.0 is the blue light. Because blue light has a shorter wavelength than red light. So we know Roy G. Biv, where violet is the shortest and then red is longer. So basically, they want you to identify that this is the longer one, so this must be red, and this is the shorter one, this must be blue. So shorter wavelength, hence blue. There you go. And you can just say that it is within the range approximately of blue light. That's why you write it. Right. Speed of light in a vacuum is 3 times 10 per 8 meters per second. Calculate the frequency of blue light. So that's pretty straightforward. You just do the formula, use the formula V is equal to F lambda. Okay, V is equal to F lambda. So 3.0 times 10 to the power 8 is equal to frequency, which we're supposed to find, and lambda of blue light. So that's going to be 5.0 times 10 to the power minus 7. So F is equal to this divided by that. So that gives us 6.0 times 10 to the power 14 hertz. So 6.0. There you go. Done. Let's move on. Last question. Average orbital speed v of an object in a solar system is defined by the equation v is equal to 2 pi r by t, basically circumference by time. Define the terms r and t in this equation. So r is the radius. So if you have an orbit, say this is a planet going around a star, then r is this distance. This is r. And the time required to complete one cycle is time. So you could say r is the radius. Radius of what? If you just say radius, it won't work. Radius of the orbit. Because if you just say radius, it might mean radius of the planet, radius of something else, blah, 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 blah. It is the time required to complete one orbit. Time required to complete one orbit. There you go. Average orbital speed of Saturn is 9,600 meters per second. Explain why the orbital speed is an average value. Because the orbit of the star is not perfectly circular, it's elliptical. It's like this. So it's going to be faster in some places. It's going to be faster here, and it's going to be slower when it's further out, right? So that's why we have to take an average of these speeds. So what you write is the orbit is not circular, it is elliptical. The speed varies, so orbit is elliptical. R varies, hence V varies. And if you want to, you can say a little more that, like, if R increases, then V decreases, and so blah 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 blah. Right, let's move on. Saturn is 1.4 10 power 12 meters from the sun. Show that one Saturn year is approximately equal to 30 Earth years. So we do the calculation. We've got the radius and we've got the speed. So we can find the time for one orbit in seconds, right? So how do you do that? Let's go ahead. V is equal to 2 pi r by t. So 2 into pi into r, which is 1.4 times 10 to the power 12. If I'm not mistaken, yes, that's it. And divided by t, the velocity is 9,600. So we can just, what we can do is we can just flip this around, and this becomes 9,600 is equal to t, right? And then you solve to find t. This answer, this value, is going to be 9.2, oops, 9.2 times 10 to the power 8 seconds. So you divide this by the number of seconds in 1 year, which is 1 year, 365, into number of hours in a day, 24, into number of minutes in an hour, into number of seconds in a minute. So if you do this calculation, you should get, all right, and that gives us 29.17. 29.173, blah, blah, blah. So you can write 29.2 years, which is approximately 30 years. So there you go. That's it. End of paper. I hope that explains all of the questions that you had. And if you have further questions, go away. Thank you, everyone. Bye-bye. Take care.